You may have heard of something called Faraday's law of induction. Some of you may even have played around with it in science class. Generally, it's demonstrated with a coil of wire and a magnet. And you pass the magnet through the wire, and the changing magnetic fields induces an electric current in the wire. This discovery helped us unite the forces of electricity and magnetism into something that we now understand and love as electromagnetism. Now imagine that you could unite the forces of electromagnetism with the force of gravity. And as Einstein told us, gravity is nothing more than the bending and rippling of space-time. So what if you had an electromagnetic source of energy so powerful that you could literally warp the space around you, expand it behind you, contract it in front of you, through the power of science? With a little sprinkling of imagination, you will have created a tidal wave of space that you could surf faster than the speed of light. What would you do with such a marvelous engine? I think I know. I think you would venture out into space, the final frontier. Explore strange new worlds, seek out new life and new civilizations. Boldly find yourself under a pile of triples. You'd be an explorer, going where no one has gone before, and all the while making new friends, sharing fond memories, and learning what it means to be human. This was the vision of a man named Gene Roddenberry, who in 1964 submitted a proposal to NBC Studios for a new television show that he called Star Trek. And from Star Trek's very inception, Gene Roddenberry knew that science was going to be at its core. In fact, in his original proposal, he wrote about an equation that was penned by astrophysicist Frank Drake just a few years ago. This equation looks like that. It's meant to organize our knowledge and our ignorance about the cosmos in an attempt to estimate the number of intelligent, transmitting civilizations in the galaxy. Thing is, in 1964, you couldn't just Google Drake's equation. In fact, Gene Roddenberry had no idea what Drake's equation looked like. So under the pressure of the studio to submit his proposal on time, he just scribbled something random and submitted it. Luckily, the studio executives at NBC also had no idea what Drake's equation looked like, and Star Trek was approved. Now, much later, Frank Drake would actually come on board Star Trek and scientifically advise an episode. And he was shown this fictitious equation of his that Gene Roddenberry had written. And he just laughed out loud. He said, "Oh, Gene, don't you know that raising something to the first power is simply itself? Why would you even write that?" So this is what Drake's equation actually looks like. Again, it's trying to estimate the number of transmitting civilizations in the galaxy, and it multiplies a bunch of terms together, and we don't have time today to go through all of them in detail, but suffice it to say, the last four terms shown here in red are highly uncertain. It's difficult to know, for instance, what the probability is for the emergence of life on a planet, or the lifetime of a transmitting civilization. These are things that we still have no good grasp of. But the first three numbers, shown here in blue, are astrophysical numbers. They're numbers that we can know today, thanks to breakthroughs in astrophysics. So if we take those first three numbers and multiply them together, we would get the number of Earth-like planets in the galaxy. And that would be the number of stars in the galaxy multiplied by the fraction of those stars with planets, multiplied by the number of Earth-like planets in a planetary system. Now, Gene Roddenberry, back in the 60s, did not know what this number was. There was no way for him to know. But he did know that this number was going to be huge. Because the number of stars in our galaxy is literally astronomical. So when you figure out what this number is, you have a choice to make about how you are going to feel about it. Are you going to feel small because you're just one life form on a tiny mote of dust floating in space? Or are you going to feel large because you're a part of this grand evolving cosmos? And special because no matter what else is out there, despite all of those possibilities, there's still just one, and only one, of you. Now, this is the kind of philosophizing that Dr. McCoy brought to Captain Kirk in an episode of the classic Star Trek series called The Balance of Terror. In this episode, Captain Kirk is pitted against a Romulan commander equally as formidable as him. And Kirk is feeling the draining weight of Starship command. He's second-guessing his every move. He just wants vacation. And Dr. McCoy, being his friend, comes up to Kirk and shows him the mathematical reality of the universe to snap his captain back into action. Let's take a look at that scene.
I wish I were a long sea voyage somewhere. Not too much deck tennis or frantic dancing. No responsibility. Why not? Look around the bridge. I see the men waiting for me to make the next move. Bones. What if I'm wrong? Captain, what do you expect an answer?
I've got one. Something I seldom say to a customer, Jim. In this galaxy, there's a mathematical probability of 3 million Earth-type planets. And in all of the universe, 3 million galaxies like this. And all of that, perhaps more. Only one of each of us. Don't destroy the one named Kirk.
Where's my... Thank you. All right, so Dr. McCoy says there are 3 million Earth-type planets in our galaxy. Let's see how right that estimate is. So today, we know that there are about 200 billion stars in our galaxy. Now, this is not an exact figure, it's an order of magnitude estimate, but it's sufficient for our purposes. Thanks to the Kepler Space Telescope, the most powerful planet-finding device in all of human history so far, we know now that the fraction of planets, the fraction of stars that have planets, is approximately 1. That is to say that almost every star that you can see in the night sky has a planet going around it. And thanks to the hard work of astrophysicists around the globe, we now know that the occurrence rate of Earth-sized planets in the so-called Goldilocks zone, and I'll go through what that means in just a second, is about 20%. This is an astounding number. And if you multiply these 3 things together, you get something like 40 billion. All right, so a billion is 1,000 times more than a million. So Dr. McCoy was way off in his estimate. He was off by a factor of over 10,000. But we can forgive Bones, because as he would love to remind us, damn it, Jim, I'm a doctor, not an astrophysicist. All right, so let's talk a little bit more about what it means to be an Earth-like planet. This is our solar system, our sun with the three largest terrestrial planets in it, Venus, Earth, and Mars. And generally, what we talk about when we talk about Earth-like worlds is terrestrial planets within the so-called Goldilocks zone. This is the range of distances from a star for which a terrestrial planet could have liquid water on its surface. Get too close to the star, like Venus, and your water will boil away. Get too far away, like Mars, and your water will freeze into ice. Now, scientists can also calculate what is called a tidal locking radius. This is a distance from the star within which your planet will be tidally locked. And in general, what that means is that a planet will have a permanent day side, a permanent hemisphere that always faces the sun, and the other hemisphere will always face away, the perpetual night. So it turns out that our sun is a slightly larger star than average. Most of the stars in our galaxy are smaller, dimmer, and redder than our sun. And you can calculate how the tidal locking radius and the Goldilocks zone change with stellar size. So as the star gets smaller and less massive, it has less gravity to do its tidal locking. So the tidal locking radius moves closer to the star. Also, as stars get smaller, they have less luminosity. Their temperatures are lower, so the Goldilocks zone also moves closer to the star. And in fact, these two quantities cross each other, such that if you are a terrestrial planet in the Goldilocks zone around one of the smallest, dimmest, reddest stars, you are almost certainly tidally locked. There's an example of a tidally locked planet in Star Trek. Its name is Remus, and the Remans, who inhabit this world, can't live on the day side because it's far too hot there, and they can't live on the surface of the night side either because it's far too cold. So what the Remans do is they build their cities down into the ground to take advantage of the geothermal heat. Are all tidally locked planets going to be doomed to be like Remus, to be uninhabitable on its surface, and the only possibility for life to be eking out an existence in the subsurface? Not necessarily. What if we gave Remus an atmosphere, or even better, an atmosphere and an ocean? What do atmospheres do? Well, to find out, let's go back to Earth, the planet that we know best. It turns out that atmospheres in general circulate heat, redistribute the heat. And Earth gets more sunlight by its equator than by the poles, and the atmosphere serves to create these giant convection cells that take excess heat from the equator and dump them at the poles, making the poles warmer than they would be otherwise. Now, the poles may be very, very frigid and inhospitable for you and me, but they are still extremely habitable environments. Just ask the polar bears or the penguins. Turns out that scientists are able to apply the same physical laws and run the same computer models for atmospheres around other planets, including around tidally locked worlds. And it turns out that atmospheres for tidally locked worlds will serve to redistribute the heat from the bright, hot day side to the cold night side. Such that a tidally locked planet with an atmosphere and an ocean may look something like this. We call it an eyeball world, with a hemisphere in day, with a temperate climate, plenty of clouds to reflect the sunlight back into space so that it doesn't get too hot, and an atmosphere and an ocean that will bring heat to the night side, where it will still be cold, but not uninhabitable. There can still be life forms that can adapt to those conditions. Well, somehow, Remus lost its atmosphere. And indeed, this may happen for a great number of tidally locked worlds huddled close to their host stars. And it's the job of the next generation of telescopes, including the James Webb Space Telescope, to find out and characterize whether these tidally locked terrestrial planets do indeed have atmospheres and perhaps even oceans that can redistribute their heat around and make their surfaces habitable. So going back to Remans, Even though they are subsurface dwellers, they still venture out into space, and they have made an alliance with their Romulan cousins and formed a vast star empire that poses an existential threat to humanity. And in order to overcome this threat, we must make alliances with other spacefaring civilizations in the galaxy and create the United Federation of Planets. This is an alliance between humans, Vulcans, Andorians, and others. So where do the Andorians come from? Well, they come from Andoria. Not this world, but this world. That's right, Andoria is a moon of a gas giant planet. Very unlike our moon, which is basically a hunk of rock in space, but more akin to the real-life icy moon of Jupiter named Europa. And we know that Europa has a massive subsurface ocean of liquid water. In fact, if you took up all the water on the surface of our planet and rolled it up into a ball, it would be smaller than if you took the water in the subsurface ocean of Europa and rolled that up into a ball. This is an astounding fact. How can Europa sustain a liquid water ocean so far away from the sun? To answer that, let's take a closer look at the system that Europa is in. It is one of a quartet of satellites orbiting Jupiter, large satellites that we call the Galilean satellites, Io, Europa, Ganymede, and Callisto. It turns out as these satellites do their dance around Jupiter, they are continuously squished and squashed by Jupiter's strong gravitational field. And this squishing and squashing deposits heat into their subsurfaces. We call this tidal heating. And it turns out that Io, being the closest to Jupiter, experiencing most of this squishing and squashing, receives too much tidal heating to be habitable. But it does make Io the most volcanically active object in our solar system. Ganymede and Callisto, on the other hand, receive far too little tidal heating to be astrobiologically relevant, but Europa gets just enough. This is like a new Goldilocks zone, if you will, to maintain a liquid water ocean. So when we say Europa is a good place for life, we need to ask ourselves why. What does life do? What does life need? And luckily I have all of you in front of me as prime examples of living creatures to remind me what life does. You're all breathing right now. You're also all digesting your food and your drinks. And our metabolisms connect the food and drinks that we eat and drink to the oxygen in the air that we breathe. That is how we gain energy for us to live. So are there food sources and quote-unquote air sources on Europa? Turns out that we think there are. Deep under Europa's ocean, we suspect that there are hydrothermal vents. And by studying the vents here on Earth, we know that they are a rich source of chemical energy for life. In fact, some of the most productive areas of our biosphere is located at submarine hydrothermal vents, completely devoid of sunlight. All right, so there's good chemical food to eat on Europa. How about things to breathe? Europa, it turns out, doesn't have an atmosphere, or not a very substantial one, but it does have this ice shell that is constantly being bombarded by radiation. Radiation from the sun, radiation trapped in Jupiter's magnetosphere, some radiation that is originating from the volcanically active sister moon Io. And what this radiation does is it processes this ice, creates chemicals called oxidants, chemicals that act like oxygen, and because the tidal squishing and squeezing creates cracks and breaks and perhaps even subduction in the outer ice shell, these oxidants could flow into the ocean where they might be consumed by life. So this process makes Europa an extremely, potentially habitable environment. And similar processes could be making the fictional Andoria from Star Trek habitable as well. Now I have one last story to share with you, my favorite science and Star Trek story, in fact. It concerns a real-life scientist named Carolyn Porco. She is a planetary scientist and was the imaging lead for the Cassini spacecraft, which spent over a dozen years orbiting Saturn. In addition to being a very prolific and excellent scientist, Dr. Porco is a very passionate speaker. And she was giving a TED Talk once when she was approached by a man with curly dark hair and thick glasses. And the man said, "Hello, Dr. Porco. My name is J.J. Abrams, and I need your help." And Dr. Porco said, "Sure, how can I help you?" And J.J. said, "I am writing a script for a reboot of this classic science fiction show called Star Trek." And Carolyn said, "I love Star Trek. How can I help?" And JJ said, "Okay, I've got a problem with the plot. You see, I've got the Romulans attacking Earth, and they're about to create a black hole where Earth is and destroy Earth. So the Enterprise needs to swoop back into the solar system and save the day. But they can't let the Romulans know that they're coming. Where can I hide a starship in the solar system?" Carolyn just smiled and she said, "JJ, I have the perfect place for you. And this is the result."
Whatever the case, we need to get aboard Nero's ship undetected.
Just go in there, guns blazing, shit. I'm telling you, the math doesn't.
We could have to check out. What is it?
Based on the radar's course from Vulcan, I had projected that Nero will travel past Saturn. Like you said, we need to stay invisible to Nero or he'll destroy us. If Mr. Scott can get us to work factor 4, and if we drop out of work behind one of Saturn's moons, say Titan, the magnetic distortion from the planet's rings will make us invisible to Nero's sensors. From then, as long as the drill is not activated, we can beam aboard the enemy ship.
Hi, that might work.
Wait a minute, kid. How old are you?
17, sir.
Oh, goody, 17.
Doctor, Mr. Chekhov is correct. I can confirm his telemetry. If Mr. Sulu is able to maneuver us into position, I can beam aboard Nero's ship, steal back the black hole device, and if possible, bring back Kathryn Janeway.
Won't allow you to do that, Mr. Scott.
Romulans and Vulcans share a common ancestry. Our cultural similarities will make it easier for me to access the ship's computer to locate the device. Also, my mother was human, which makes Earth the only home I have left.
I'm coming with you.
I would cite regulation, but I know you will simply ignore it.
See? We are getting to know each other. Prepare the trout.
All stop. In 3, 2, 1. Give me 1/4 impulse burst for 5 seconds onto the lesser thrusters on my mark.
Aye.
5. Transporter room.
We are in position above Titan.
Really? Fine job, Mr. Silly. Well done.
All right. Thank you, Brett. Okay, so that is the story of how J.J. Abrams asked for help from Dr. Carolyn Porco and how we have a real-life planetary scientist to thank for the Enterprise swooping in to Saturn's moon Titan's atmosphere to save the day. And this was brilliantly written into the script as an idea that was concocted by the young Pavel Chekhov. Now, I do have one scientific problem with what happens here. Of course, Chekhov mentions Titan, and then he goes on to blabber something about how Saturn's magnetic field will get distorted by the rings. The rings don't actually do that, but we can forgive him because he's only 17. So what makes Titan's atmosphere such a great place to hide a starship? Well, it all starts with the fact that Titan's atmosphere is full of this molecule called methane, which is a molecule composed of 1 atom of carbon and 4 atoms of hydrogen. It turns out that if you shine ultraviolet sunlight on methane, you can pop off one of the hydrogens, creating what is called a methyl radical, and the hydrogen will float on off into space because it's so light. Now, if 2 methyl radicals find each other, they may notice that each other is missing a crucial link, and they may inch closer and closer and closer. And form a new molecule called ethane. And it's this process repeated over and over and over again that creates longer and longer chain molecules in Titan's atmosphere. Propane, benzene, propyl, nitrile, they've all been observed, and they create this organic haze that completely shrouds Titan and makes it a fantastic place to hide a starship. So, I'm pretty happy in general with how science is portrayed in Star Trek. There is, though, one little thing that bothers me sometimes, and it's that often the science officers in Star Trek are portrayed as being a little odd. It seems like in order to be a science officer in Star Trek, you either need to have suppressed emotions, or be annoyingly right all the time, or be childishly robotic, or a cyborg perfectionist, or be a symbiont with a 300-year-old creature in your gut. Now, don't get me wrong, all of these traits make these characters extremely endearing to watch, but they can also make these characters a little bit hard to relate to as an average human being. So I want to end this talk by reminding you about another very important character in Star Trek, a character who is not generally associated with being a science officer, but who is definitely still a scientist at heart. And that character is Kathryn Janeway. Kathryn Janeway was born in Bloomington, Indiana. Her hobbies include drinking coffee, playing tennis, going skiing, and learning new languages. And her Starfleet record shows that she went on to become one of the greatest officers in the entire Federation. She was the chief science officer aboard the USS Albatani before assuming command of the Starship Voyager, leading her crew home 70,000 light years back to Earth, where she was then promoted to Vice Admiral of Starfleet Command. Kathryn Janeway is just a normal human being. Her story can be any of your stories. So I want to now speak to the younger folks in the audience. If you haven't had a chance yet, maybe go watch some Star Trek. Maybe you'll like it. Maybe you'll connect with one of the characters. Maybe you'll feel inspired. Maybe you'll even feel inspired to pursue a career in science. Because as we have seen today, the power of science, plus the power of imagination, can take you anywhere. Your captain's chair is waiting. The future is yours. And I'll see you out there. Thank you. Before I take questions, as some of you know, there is a new Star Trek series on the air, Star Trek Discovery. I didn't include anything from Star Trek Discovery, mainly because this talk went way over time, and also I don't want to spoil it for any of you if you haven't seen it. But if you're interested in learning more about the science from all aspects of Star Trek, including this latest show, you can check out my podcast, Strange New Worlds. You can find it on any podcast app, and you can also follow me on Twitter. Thank you very much, and I'll take your questions if there are any. Okay, right there.
What's your favorite Star Trek series?
What's my favorite Star Trek series? It's like choosing, which is your favorite child. I can't decide. But I grew up watching Voyager, so I definitely will go with that one for now. Yeah. Right there.
Have you ever mixed
any problems by reversing the polarity of everything?
Yeah, that's like 23rd century duct tape. Absolutely. That's fixing the polarity, fixing something by by reversing the polarity. It's like a Star Trek trope. It fixes everything. Yes, you again.
Yeah, right. With Titan having such a thick atmosphere, is there any water or chance for life on that moon?
I love that question. Titan has a thick atmosphere, so is there a chance for life on Titan? And also, is there water on Titan? The answer is there's lots of water on Titan, but Titan is so far away from the sun and it doesn't receive so much tidal heating like Europa that all of the water is frozen solid as ice. It makes the bedrock of Titan. Titan does have liquid methane and ethane seas. And so you can imagine a wildly different kind of biochemistry that could exist in those seas. I don't have time to go into all the details, but Titan is a very exciting place for astrobiology because there could be life there that is completely different from the life that we know that runs off of liquid water. Yes?
So what is the possibility of non-carbon-based life?
What is the possibility of non-carbon-based life? So you may be a fan of the Horta or the crystalline entity. Yeah, so that's a great question. I would say that silicon-based life is a possibility, but not at the temperature and pressure regime that we are used to here on Earth. The reason is because if you think of the way that silicon likes to bond to things, for instance, we'll just take two types of carbon that is accessible to biology right now, carbon dioxide and methane. If you take the silicon equivalent, silicon dioxide is quartz, so that's rock, and it forms these long chains and frameworks that is highly inaccessible. The silicon equivalent of methane is called silane, and it's SiH4. And, this is getting kind of technical, but basically, did you also ask me a question about reverse polarity? Okay. The polarity of the silicon-hydrogen bond is reversed from the carbon-hydrogen bond, which makes silane extremely reactive, and in fact, it combusts spontaneously, which makes it also inaccessible for life. So yeah, silicon-based life at our normal pressures and temperatures not going to fly. Great question. Yes?
I guess the projection of the non-tidal planet. The projection of the non-tidal planet was the ice outside of the water on the other side, that ice. It showed a huge storm in the middle.
Yeah.
I don't know, I'd like to hear a little bit about that.
Yeah, absolutely. So what drives storms? Storms basically are made when water evaporates, right? And so that planet will be receiving constant sunlight at its equator right beneath where the sun is, like the most direct line of sight from the sun. And so there will be a huge storm over there, and if you simulate the clouds on that planet, you'll realize that because the clouds pile up at that point, they'll actually reflect most of the sunlight away, which keeps that side of the planet from not being too hot. So the clouds are extremely important for the habitability of those worlds. Great question. Okay, great. Thank you all.